Yeah, so in this video we'll discuss about the common emitter characteristics. Okay, so like in the common base characteristics, the base was grounded and it is the same, it is common between input and output. Okay, in common emitter characteristics, see, your emitter would be grounded and it would be common between input and output. Okay, so let us try to analyze what the input voltages and currents are and output voltages and currents are. So here this would be your input side. Okay, and this is your output side. Okay, so at the input side, if you see, the current is nothing but IB and the voltage is nothing but VBE. Okay, similarly at the output side, you see the current is nothing but IC and the output is voltage is VCE. Okay, so like with the common base characteristics, okay, we'll also go with a set of input characteristics. Okay, so that is IB versus VBE for different values of VCE, and we also have a set of output characteristics, that is IC versus VCE for different values of IB. Okay, for different values of IB. Okay, right, so let us try to understand the input characteristics first. Okay, so this is your input characteristics. Okay, so like I mentioned, it is between IB and VBE. Okay, for different values of VCE. Okay, so this curve is for VC is equal to 0 volts, and this curve is for VC is equal to 10 volts and 20 volts. Okay, so as VCE is increasing, okay, if you see here, VCE is increasing. Okay, what is, so for suppose let us take at this particular value of VBE, say 0.8. Okay, you can see that for VC is equal to 0 volts. Okay, we have approximately 40 microamps of base current. Okay, for VC is equal to 10 volts, we have 20 micro amperes of base current, and for VC is equal to 20 volts, you see it is roughly 10 microamps. Okay, so as the voltage VCE is increasing, okay, we see that the base current is reducing. Okay, so let us try to understand that the similar phenomena was occurring at the input characteristics of the common base configuration as well. Okay, but at that time I told you that I'll explain this phenomena in common emitter characteristics, so I'll explain it now. Okay, right, so what is this VCE? Okay, so VCE is nothing but voltage is always difference, right? So this is nothing but VC minus VE. Okay, so but also VCE also can be written as okay, VCB plus VBE. Okay, this should make sense, this is algebra. Okay, so this is nothing but VC minus VB, and VB is nothing but VB minus VE. Okay, if you see that this is nothing but VC minus VE, and VC minus VE is nothing but VCE. So there is no harm in writing VCE as a sum of VCB and VBE. Okay, now for suppose at this point, let us say VB is constant. Okay, so VB is constant at 0.8 volts. Okay, at VB is constant at 0.8 volts, but as VC is increasing from 0 to 10 to 20, okay, what should happen appropriately? VCB also should increase. Okay, because VB is kept constant over here, so VCB should increase. Okay, but when VCB is increasing, what is happening to IB? IB is decreasing. Okay, IB is decreasing. Why is the behavior occurring? Let us try to analyze. Okay, okay, so we know that IB is proportional to exponentially, okay, VB by VT. Okay, we have seen this behavior in the transistor lecture. Okay, so that is why because IB is proportional to e power VB by VT, so that is why we have the input characteristics similar to, okay, forward diode characteristics. These are nothing but forward diode characteristics. That should make sense first of all. Okay, this is because IB is proportional to e power VB by VT, and this is nothing but characteristics of diode in forward region. So that is why the characteristics are looking like this. Okay, now let us try to understand why when VCB is increasing, IB is decreasing. Okay, so let us take the transistor. Okay, NPN. Okay, Okay, sorry for that. Okay, so we know that the base region, okay, the width of base is much lesser. This is emitter, base and collector. We know that for active region, emitter base junction should be forward biased and the collector base junction should be reverse biased. Okay, now so let us see what is happening over here. Okay, when VCB is increased, okay, when VCB is increased, okay, the collector base junction becomes more reverse biased. Okay, when VCB is increased, what happens is collector base junction becomes more reverse biased. That means the depletion region width of the collector base junction is even more. Okay, remember, as the reverse bias increases, the depletion region width also increases. Okay, as the depletion region width is increasing, what is happening to the base? The effective base width, see, so the base was already smaller, but because of the increase in VCB, the depletion region width increased and the effective base width is even smaller now. Okay, the effective base width is so small now. Now how should this affect IB? Okay, we know that these electrons enter the base. Okay, and IB is nothing but the recombination current. We know that from the transistor lecture. IB is recombination current. Okay, what is recombination current? These electrons, okay, from the emitter, they recombine with the holes of the base and it forms a current. Okay, that is nothing but IB. Now what is happening when VCB is increasing? Okay, the depletion region width is increasing. Okay, that is nothing but resulting in lesser base width. Okay, that is called effective base width is reducing. Okay, effective BW for base width is reducing. Okay, when effective base width is reduced, okay, what happens is very few electrons recombine with holes over here. Okay, very few electrons recombine with holes. Okay, when recombination is reducing, what reduces? Of course, when recombination is reducing, IB, which is a direct product of recombination, IB decreases. Okay, and that means more and more electrons, these external injected electrons, reach the collector. Okay, that means IC also increasing. Okay, so what is happening when we increase VCB? When we increase VCB, okay, the depletion region width of okay, the depletion region of a common base junction is increasing. That is resulting in effective base width reducing. When effective base width is reducing, IB is reducing. When IB is reducing, okay, IC is also increasing. So this is how when we increase VCB, IB is reducing. That is what is being shown here. Okay, when you increase VCE, okay, at a particular point of VBE, VCB increases, and when VCB increases, IB reduces. So that is what the family of curves is showing over here. So the same reasoning applies for input characteristics of the common base configuration. The same reasoning applies. Okay, so now you go back to that lecture and try to connect the dots. Okay, so this is how the input characteristics look like for a common emitter configuration. Now let us look at the output characteristics. We know that the output current is IC, okay, and the output voltage is VCE, okay, and we plot this for different values of IB. Okay, we plot this for different values of IB. Okay, so we know that IC and IB are related by beta, and typical value of beta, like I told you, is between 100 to 150. Okay, so we know that beta is equal to IC by IB. Okay, and we know that it is typically around 100. Okay, now let us try to understand. Okay, see, this looks similar, but see, this region has some curve over here. Let us try to understand what is happening over here. Okay, so at this point, okay, we know that VC is equal to 0. Okay, at this point VC is equal to 0, but we know that VC is equal to VCB plus VBE, and VB is nothing but the input voltage, and we know that the emitter base junction has to be forward biased. That means VB from the constant voltage model, we can set that VB is at 0.7 volts. Okay, so this VB, when emitter base junction is forward bias, this is set at 0.7 volts. But when VC is equal to 0, what does that make VC be? Okay, when VC is equal to 0, okay, that makes VCB is equal to minus 0.7 volts. That results in a VCB of a negative value. When VCB is negative, okay, that means your collector base junction is not forward biased anymore. Okay, when VCB is a negative value, what happens is the collector base junction is not reverse biased anymore. What happens is when VCB is negative, the collector base junction becomes forward biased. Okay, the collector base junction becomes forward biased. Okay, and that is why you can see, okay, that is why you can see some kind of weird behavior happening. Okay, till here. Okay, and when VCB, okay, is equal to or rather when VCE, the output voltage VCE is equal to 0.7. Okay, what happens is, okay, VC is nothing but VCB becomes 0 and VB is a constant voltage. Okay, 0.7. Okay, so what is happening to your VCB here? VCB is 0, and when VCB is equal to 0, that is when your collector base junction is reverse biased again. Okay, remember we want it to be in active region. Okay, all your formulae, alpha, beta, everything depends on the active region. So those all formulae are derived for active region. Remember, alpha is equal to IC by IE and beta is equal to IC by IP. Remember, these apply only for active region. Okay, so for VC very small value, okay, from 0 to 0.7, what happens is, okay, your collector VCB is a negative value, and when VCB is a negative value, collector base junction is reverse bias. Collector base junction is forward biased rather. Sorry for repeatedly making that mistake. When VCB is negative, collector base junction is forward biased. When collector base junction is forward biased, you are not in active region. When are you in active region? You are in active region when emitter base junction is forward biased and collector base junction is reverse biased. So when VC is very small value, okay, collector base junction is actually forward biased. So that is why, yeah, all these alpha beta formulae, these don't apply anymore when collector base junction is forward biased. Okay, so once after it crosses around 0.7, okay, so your collector base junction goes back to being reverse biased. Okay, and the transistor comes into the active region. See over here. Okay, so before this line and after this line it goes into active region. So active mode, it is shown active mode, and all your alpha beta apply. For suppose beta is 100 over here. Okay, if you see for IB is equal to 10 microamps, if beta is 100, IC is equal to 10 micro into 100, that should give you 1000 microamps. So 1000 microamps is equal to 1 milliamp. Okay, see, that is what it is showing here. Okay, around 1 milliamp. But you can see there, this is not flat line. Okay, if it were flat it would look something like this, but it rather has some slope. The slope is also understandable. Why? Because as VC is increasing, what is happening? We have seen in the earlier discussion, as VC is increasing, okay, VCB is also increasing, because VB is a forward bias diode and it is more or less stuck between 0.7 to 0.8 volts. Okay, so when VC increases, VCB increases. Okay, and when VCB increases, we have seen that IB recombination reduces and IC increases. So that is how your output characteristic has a small slope over here. Your similar characteristic for CB, it was flat. Okay, your CB was flat, isn't it? But this has a small slope. Why? Because as VC increases, IC also increases. So that is what is being shown here. But once it is in active mode, its value roughly can be calculated from beta. Beta is IC by IB. So that is what is being shown here. If IB is equal to 20 microamps, Okay, IC is equal to 20 micro into 100 will give you roughly 2 milliamps, roughly 2 milliamps. But this slope is because of that effective base width reduction that I have discussed earlier in the lecture. Okay, and until this region, okay, both junctions are forward biased. Collector based junction is also forward biased and emitter based junction is also forward biased. So that region is called saturation region. Okay, this region is called saturation region. And we know the condition for active region: collector based junction should be reverse biased and emitter based junction should be forward biased. This is the condition for active region. Okay, so in your output characteristics of CE configuration, okay, you have two modes. This is the active mode, okay, above, when VC is above 0.7, and when VC is between 0 to 0.7, both junctions are forward biased. Okay, your transistor is said to be in saturation region. All these formulas do not apply anymore. That is, the common emitter current gain beta and the common base current gain alpha, they don't apply anymore. Okay, so this is the most widely used configuration. Okay, CE is the most widely used configuration. Okay, so when it is set in active region, okay, when it is in active region, that is collector based junction reverse biased and emitter based junction forward biased. Okay, so you can see that it works as an amplifier. Okay, that would be quite apparent if you see the input current over here. What is input current? IB is 10 microamps over here. What is the output current? 1 milliamp. Okay, you have an amplification gain of 100 over here. You can see how common emitter is working as an amplifier, current amplifier over here with the simple example over here. Okay, so when your CE, okay, if you in CE configuration is most widely used. Okay, if you wanted to use it as an amplifier, you have to use its active region. Also, another application of CE configuration is switching. Okay, so if you want to use the transistor as a switch that is on and off, okay, you have to make use of the saturation region and cutoff region. Cutoff region is when IB is equal to 0. Okay, so basically this line over here, that is when your IC is also very small value. Okay, when IB is 0, IC is also very small value. Okay, so in the cutoff region also what happens is your collector based junction is reverse biased and even your emitter based junction is reverse biased as well. Okay, so when you use these two regions, the cutoff region and the saturation region, okay, then your transistor switches, that is, it works as on and off. On means as a short circuit and off means as a open circuit. Okay, that is again a lengthy discussion, is not in the scope of our syllabus, but you have to remember that CE configuration is widely used. Okay, so if you set it in active region, it works as an amplifier, that much you have to remember. And if you put it in either or rather if you are making use of the saturation region and the cutoff region, okay, you are using your transistor for switching, or you are using as a you are using the transistor as a switch. Okay, so this is the most widely used configuration of a transistor, be it NPN or PNP. Okay, right, so that should end the input and output characteristics of common emitter configuration.